So the problem that you're going to do for this quest is to look at angular momentum and its conservation. So remember, linear momentum was mass times velocity, and angular momentum we're going to use the symbol L for. If I look at the rotational equivalent of m, it's I. If I look at the rotational equivalent of v, it's omega. So the angular momentum, instead of being m times v, is I times omega. And also remember, Newton's second law was that the sum of the forces, the net force, was equal to the rate of change of linear momentum. So here, for rotation, we're going to say that the net torque is equal to the rate of change of angular momentum. And just like we did for linear momentum, for angular momentum, if the net torque is zero, so the left side is zero, that means the right side is zero, so that means that the change in angular momentum is zero, so the angular momentum is constant. So if there's no net external torques making something speed up or slow down, then the total angular momentum is constant. So I times omega will be conserved. So I times omega in any combination, if I increase I, then omega will decrease. If I decrease I, omega will increase, and vice versa. So this is the reason why, for example, if you're trying to walk a tightrope, you spread your arms to balance, and that increases your I, and that will decrease the rate at which you spin as you go out of balance, and so you're less likely to overbalance. Also, when you're riding your bicycle, if you're going quickly, you're less likely to tip over because your angular momentum is conserved. You see this in everyday life when you watch sports on TV. If you see a figure skater spinning with her arms out and then she pulls her arms in, when she pulls her arms in, she's decreasing her moment of inertia because the amount of mass that she has at a large distance from her axis of rotation decreases, and so then she starts to spin faster. Same thing for a diver. When a diver curls up into a ball, they decrease their moment of inertia and then they spin very quickly. So I times omega is constant. So if you increase I, omega decreases. If you decrease I, omega increases. So let's do a figure skater calculation. So a figure skater increases her spin rotation rate from 0.5 revolutions per second to 3 revolutions per second by changing the position of her arms. So omega initial is 0.5 revolutions per second, and that's not exactly the right units, right? Remember, it should be radians per second, but it turns out we can leave it in these units as long as we're being consistent. If you want to, you can change it to radians per second by using 2 pi radians is 1 revolution. But as long as I'm consistent and I keep it in the same units, it doesn't matter. So omega initial is a half, omega final is 0.3. She changes the position of her arm. So if her initial moment of inertia, I0, is 4.6 kilogram meters squared, what's her final moment of inertia? Well, what's my equation? I0 omega 0 equals I final omega final. The product of the moment of inertia and omega stays the same. So I have everything on the left side. I have omega final. I want to find I final. So it's just very simple algebra. I final is I0 omega 0 over omega final. Okay, so I0, 4.6. Omega 0 is 0.5. Omega final is 3.0. Okay, so what do we expect? Before we get our number, what do we expect? Well, if she sped up, so she went from low to high, if she sped up, she must have decreased her moment of inertia. So I expect that my I final should be smaller than 4.6. And if I put in my numbers, I get 0.77 kilogram meters squared. So indeed, she sped up because her moment of inertia decreased. Okay, so why didn't I have to change the units? Well, you see here, I ended up doing a ratio of omega 0 to omega final. So any conversion factor would have canceled out. So I don't need to do the conversion. let's do a slightly more complicated one. So now I have a record, and the record has a 0.10 kilogram meter squared moment of inertia. So just for the record itself. And it's rotating at 10 revolutions per minute. And again, we're going to do the same thing that we did in the previous problem. Revolutions per minute isn't the standard units, but because I'm going to end up having the RPM on both sides, it'll cancel out, so it doesn't matter. All right, then I'm going to take a 200-gram blob of putty. I'm going to drop it onto the record 20 centimeters from the center, and I want to know what's the new angular speed in RPM. So I want to know what's omega final. And so the question is, what did I do that would have changed the moment of inertia? Well, what I did is I put some more mass on the record, and that will increase its moment of inertia. So the new moment of inertia is going to be equal to the moment of inertia for the record, plus it's going to be equal to the moment of inertia for the putty. And what's the moment of inertia for the putty? Well, the moment of inertia for the putty is going to be the mass of the putty times r squared. Remember, that's our equation for the moment of inertia. So we're just going to do a plug and chug. So moment of inertia for just the record is 0.10. The moment of inertia for the putty is going to be mr squared. So m for the putty is 200 grams. And I need to put that into kilograms. So I divide by 1,000. So it's going to be 0.2 kilograms. And the radius, it's 20 centimeters. So r is 0.2 meters. Make sure you put everything in standard units there. And I'm going to square that. So when I plug that in my calculator, I get just a small change. 0.108 is my new moment of inertia. Okay, so the final angular frequency shouldn't be too much smaller than the initial. So now what do? I initial omega initial equals I final omega final. The same steps all the time for conservation of angular momentum. I want to find omega final this time. So I'm going to do I0 omega 0 over I final. So we've got 0.1 times 10 divided by 0.108, and I get 9.26, and to two significant figures that would be 9.3, and the units are going to be the same as for omega initial, RPM. So I increased the moment of inertia slightly, and the angular speed decreased. Okay, so the problem that I'm going to have you do is very similar. So you've got a playground merry-go-round that has a moment of inertia of 275 kilogram meters squared, and you're told that when you have the merry-go-round with a kid standing 1 meter from the axle, so that's your initial position, you have the merry-go-round plus the kid 1 meter from the center, the system is rotating at 14 RPM, and then your final condition, you're going to have the merry-go-round, but now the kid is 2 meters from the center. So you need to find the moment of inertia for initial and final, and then calculate what's the new angular speed of the system. And so think about it. Would you expect it to speed up or to slow down?